Hello again, and welcome to the last section of our unit on electric potential. And in this section, we are going to be doing a couple of basic calculations and not so basic calculations of electric potential. So to begin, we're going to start with just a point charge. So I have a 6 nanocoulomb point charge. Here he is, 6 nanocoulombs. And I want to know the electric potential 3 centimeters away. So remember, that's anywhere on the circle surrounding it, 3 centimeters away. So I have V equals KQ over R. K is 9 times 10 to the 9th Newton meter squared per coulomb squared, the same number we've been using for the last 2 units here. 6 nanocoulombs is 6 times 10 to the minus 9 coulombs. And 3 centimeters is 3 times 10 to the minus 2 meters. And there's no square here, so watch out for that. And that works out to be 1.8 times 10 to the 3rd volts. Wow. Okay. What if the charge were negative? What would change? The only thing that would change, if you think about the calculation, this would still be 9 times 10 to the 9th Newton meter squared per coulomb squared. Q is now negative 6 times 10 to the minus 9 coulombs. And this is still 3 times 10 to the minus 2 meters. The exact same numbers before with one negative sign stuck in there. So the answer is the negative of the answer that we had before. What if we had multiple point charges? What if we had multiple point charges? Now, think about just for a moment how hard this problem would be if we were working with field or force, because there's no symmetry other than the fact that we're on a circle. The angles are all different. Everything's difficult, if you will. But potential's a scalar. So that makes life a lot easier. So I'm going to begin. Remember, we're going to the center of the circle, and I give you the radius, by finding the contribution for the total potential due to each piece. So due to the negative 3 nanocoulomb, I have K, which is 9 times 10 to the 9th Newton meter squared per coulomb squared, times my Q, which is negative 3 times 10 to the minus 9 coulombs, divided by my distance, which is 0.04 or 4 times 10 to the minus 2 meters. And that works out to be negative 675 volts. I'm going to go around the circle to the negative 4 volt. So 9 times 10 to the 9 again. Negative 4 times 10 to the minus 9 coulombs for the charge. The distance is the same. And that works out to be negative 900 volts. Due to the 1 nanocoulomb, 9 times 10 to the 9. Positive 1 times 10 to the minus 9 coulombs for the charge. And still 0.04 meters. And that works out to be 225 volts. One more to do. I have the voltage due to the 2 coulomb charge. So 9 times, let's fix that. 9 times 10 to the 9th Newton meter squared per coulomb squared. 2 times 10 to the minus 9 coulombs because it was a positive 2. And we divide by 0.04 meters, and that works out to be 450 volts. So now I know the contribution to the total voltage to each of the 4 individuals, so I can find the total voltage by adding them up. And that works out to be 225 volts plus 450 volts minus 675 volts minus 900 volts, and the total voltage therefore is a negative 900 volts. And as horrible as it looked on the surface, no symmetry, angles all over the place, we didn't need to worry about that at all because voltage is a scalar. Electric potential is a scalar. It doesn't matter. For our last example, we're going to look at a charge crossing a distance. This is very similar to the example I worked in the first section with conservation of energy, and we're going to use conservation of energy here as well. And I'm going to begin by working it from the beginning, just so that you see that process again. So the first thing I'm going to do is determine the change in electric potential energy. So the change in electric potential energy will be the charge times the change in voltage, which can be written as the charge times the field times the distance. But the thing to remember is that the change in electric potential has to be negative. This charge is going to move to a lower potential energy. And to make sure that happens when we plug numbers in, we need to make sure that we have a negative here as well. When we worked the example in the first section, the negative fell out because of how we set up the potentials. We started at 0 and then we moved to a negative V. Same idea here, but writing it in this form allows me to plug in my numbers. So I have a negative sign for this times a charge of 2 coulombs. My field I'm given as 3 nanocoulombs, and the distance is 10 centimeters, which is 0.10 meters. And if you multiply that all out, you get a change in electric potential energy of negative 0.6 joules. Now we can use conservation of energy to find out how fast. Conservation of energy tells us that the initial energy has to equal the final energy. KE initial plus EPE initial has to equal KE final plus EPE final. I'm going to rearrange it so that all my EPEs are one side, all my KEs are on the other. So that gives me that KE initial minus KE final has to equal EPE final minus EPE initial, which is my change in EPE, which I found above. Okay, so rewriting that last line, KE initial minus KE final has to equal the change in elastic potential energy. 1/2 mv initial squared minus 1/2 mv final squared has to equal my change in electric potential energy. I can now plug in my numbers there. The mass was given as 0.05 kilograms. We were told it's released from rest. And here is the speed it is moving when it finished crossing the 10 centimeters. And that has to equal the negative 0.6 joules that I calculated earlier. This term goes to 0, so I don't need to worry about it. And the minus signs are going to cancel. So that's going to give me V final squared equals 2 times 0.6 joules divided by 0.05 kilograms. And if I plug that all in, that gives me V final squared is 24 meters squared per second squared, which corresponds to V final of 4.9 meters per second. Okay, this is the last example of this section, and actually is the end of this section. In the next unit, we are going to be looking at applications of electric potential to the basics of circuitry. So we're going to introduce the concepts of current and resistance and learn the connections between voltage, current, and resistance.